Alright, in this video we're going to be revisiting our fundamental theorem of calculus, our FTC, and we're going to see or kind of go through some of the concepts. Now, some of these we have already been using when we've been taking the antiderivative or when we did this graphically, but what we're going to do is in this lesson is formally get all of the concepts that you're responsible for knowing out there and in one place, and then practice them in a variety of different situations. And so what we have here on the right is two different graphs, and what our integrals are doing, we have to remember, is what they're really doing is finding the area. And when we have bounds, we know where we're starting and stopping, and so we can see the graphs are not drawn to scale to one another, but in both of them, A is the same value and B is the same value. Okay, and so what we're going to do for this first one, or what we want to acknowledge, is the bounds, right? So you should always take note of the bounds at the very beginning of an FTC problem, whether they're both numbers. We're going to see today maybe they're the same number, or is one of them x, where we need to be able to plug something in for that, or are they backwards, right? So just because it's B and A, the alphabetical sense of it doesn't matter. What is important is from the graph, we can see that, well, A is smaller. So we can see that our bounds here are reversed. So the bounds are backwards. And so what that tells us is that any area that's above the x-axis really is going to result in a negative number for that area. And it's okay to have a negative area in this sense because we're saying it's the area underneath the curve, but it's not really an area in the sense of, oh, the area of a circle. But then if our region is below the x-axis, then it should actually be positive because the bounds are being reversed. So the bounds being reversed, say I'm starting at B and I'm going over to A. And so the answer for this would be negative A. Whatever that value of that area is that's provided for us, A, we would just need to negate that. Okay, once again, we want to take a look at the bounds here, and we notice that the bounds are the same. And so if your bounds are ever the same, then your area is 0. Okay. For 3, we can see that the bounds are different numbers. They are also in the correct order, but now we have two different functions within the integral. And so what we can do is we can separate these and say that this is really the integral from a to b of f of x, and then we're going to add to that the integral from a to b of g of x, which really is just going to give us a plus r, and that would be what our answer is. Okay, so sum and difference would be the rules that we've been using there. We used that even back when we were finding the just the antiderivatives in general. When we weren't doing FTC, we were able to look at individual pieces of the integrals to determine the antiderivatives of smaller chunks of the problem. And then for 4, we can see that we have the bounds are okay. We have g of x in there, but we have this 3, and so what we can do is that's really just a constant multiple, and so we can slide that 3 out front, and then just take the antiderivative from a to b of g of x, and then just multiply whatever that area is, or whatever number that is, by 3. So in this case, we just get 3r. Because the antiderivative, or the FTC that we're evaluating here from a to b of g of x, is the area r. Okay, and in a similar sense, we're going to really combine numbers 3 and 4 here for number 6. I'm going to come back to 5 in a second. And so what we can do is not only can we separate out with the subtraction, but we can also slide those constant multiples out to the front. And so we can change this to be 2 times the integral from a to b of g of x dx, but then I'm going to subtract 5 times the integral from a to b of f of x dx, which in this case will be 2r minus 5a. And going back up here to 5, we want to pay attention to the bounds here, because we can see that one of them is going from 4 to b, and the other is going from a to 4. But we can notice that 4 is right here in the middle, maybe not in the middle, but it's in between a and b. And so what that allows us to do, or what we really have, is if I go from a to 4 of f of x dx, and I add to that 4 to b of f of x dx, this should equal the total area of A. And so when I see that A to 4 is 3, then I know that this integral here is going to be the total area minus this a to 4 of f of x dx. And so my answer overall is going to be, or what I have is 4 to b of f of x dx is going to be a minus 3. Okay, and then on the next page we can see all of them, for all of our rules formally stated out here. These are going to be just additional ones. Like I said, a lot of them we've already been using for. The only real new ones are these last two here with the interval addition or interval subtraction. And really what you want to pay attention to with these is just making sure that based off of these inequalities, the bounds are matching up the way that you think they should. And all the rest we've been using for quite a bit, whether graphically or doing the antiderivatives.